So let's go ahead and get started. So I'm going to go over the homework that we had, but before that, somebody reminded me that when I printed off the homework yesterday, for whatever reason the copy didn't make enough copies, and I'm going to blame technology for something that could have been my mistake if I pressed the wrong button, but it's always easier to blame somebody else than blame yourself. So because of that, some of you actually didn't do the homework because I didn't remember to email it. So I'm going to give everybody, instead of 3 drops, I'm going to give 4 at the end of the semester. Okay. So just to be fair to the people that I didn't get the email or didn't get the homework to in the end. Okay. So we want to go over the homework real quickly. We have quite a couple of problems to do for class today, but in order to do those, there are 2 equations that we really need to understand, and those 2 equations are the Biot-Savart Law, which says that dB is equal to mu naught divided by 4 pi times I dl cross r hat divided by r squared. So this is Biot-Savart. And then we also had Amperes Law, which said the integral over some closed loop of B dot dl is going to be equal to mu naught times the current that goes through the area that's enclosed by the loop that you drew. Okay, so the 2 problems that we had for homework were related directly to these 2 equations. The first one was some square loop of wire. I don't remember what the direction the current was. It doesn't really matter. It's just a negative sign in the end. But let's say when I'm doing this right here that the current's going to go around in the counterclockwise direction. So this is a current I. And what we wanted to do is we wanted to find what the magnetic field was at the center of this loop of wire. So in order to do this, we can actually apply what I did for the infinite wire as the example in the notes, and just change the limits of integration. But to remind you how we broke everything down here, we'll go through the whole process. And so that's to say, if this is some element dl along this axis. So dl is a vector. It points in the direction the current is going. And so this, for this portion right here, is going to be x hat dx. This is the radius of r. This is some distance a divided by 2, because this has a total length of a, and this is half of that, so this is a over 2. And then this is some arbitrary distance. Let me move my dl. So this is some arbitrary distance x, because what I'm doing is I'm defining my origin to be right in the middle, right here. And so this is my dl vector is equal to x hat dx. Okay. Now we also have our r hat points like this, and we can label what the angle is between dl. So dl points this way, and r hat's going to point this way, and so this is the angle in between dl and r hat. And so looking at the Biot-Savart Law, we already have a lot of the things labeled that we're going to need. We just need to evaluate them explicitly. So the first thing that we can do is we can find what r is. Right? We need to know what r is. And so r, if this is r, this is a over 2, this is x, r is going to be equal to the square root of x squared plus a divided by 2 squared. Okay. Now, the next thing that we need to do is we need to evaluate this cross product. dl is equal to dl cross r hat is going to be equal to the product of the magnitudes of these vectors times the sine of the angle between them times the unit normal vector that's mutually perpendicular to them according to the right-hand rule. And so the magnitude of dl is just going to be dx. The magnitude of r hat is what? It's a unit vector. 1, right? So that's just 1. The sine of the angle between them, I've already labeled what that angle is, and so what I can do is I can write this as just sine of theta times n hat. So n hat is going to be the vector, the unit vector that's perpendicular to both of these vectors that you find via the right-hand rule. And so we can remember we can find that vector by taking our fingers and pointing them in the direction of dl, and then curling them into the direction of r hat. And so if this is the direction of dl, we curl into r hat. That gives me a vector that points this way. Okay. So looking at this, we see that ultimately we're going to want to be integrating over x, and we have this sine of theta. Now, for every point along this axis, so say I have a point over here, this is a different theta than I have here, which tells us that theta actually varies as a function of x, and so we need to parameterize this in terms of that. And so when we look at this, this triangle that I have here, this is theta, this is x, this is y, this is r. Sine of theta is just going to be y divided by r. And so this is going to be equal to dx y divided by x squared plus a divided by 2 quantity squared to the 1/2, pointing out. Okay. So now we have everything that we need in order to find what the magnetic field is from one of these sides. And so we can put all of this together, and that's to say that B vector is going to be equal to mu naught divided by 4 pi times I times the integral of y dx divided by, this is r squared, this is an r here, so that gives me an r cubed, which is going to make this x squared plus a divided by 2 quantity squared to the 3/2. Okay, and then I have my vector that points like this. Okay, now this actually looks almost identical to the example that I had in the notes, with the exception of the limits of integration. I actually haven't written those in yet. So the question is, if I say that my 0 is in the middle right here, so this is where I'm saying x is equal to 0 is, where is this distribution going to start and where is it going to end relative to that definition of the origin? What do you guys think? Yeah, so this goes from minus a over 2 to a over 2, right? Because this is 0, this is a distance a over 2, but it's negative because I say this is the positive x-axis, and then it goes up to a distance a over 2. Okay. Now you could have done this a little bit differently, yeah?
Yeah, why can't you just say 0 is at the end?
You could. So if you wanted to, you could have done that. What's going to change is the way that I'm defining what r is. So if I do it like this, and I say that here's my dl, here's my r, this is my angle theta. So dl is still x hat dx. This is now the distance x, right? Because I'm defining my origin to be in this left corner. And so what that means is when I try to find what r is, I need this piece right here, right? Because that's the base of the triangle. And if this distance is the distance a divided by 2, that means that this distance here is going to be a over 2 minus x. And so that says that r, if I wanted to define my origin like this and then ultimately integrate from 0 to a, r is going to be equal to the square root of a divided by 2 minus x quantity squared. This is plus a divided by 2 squared. So you could do it like that, but you have to be careful with the way that you're defining the base of this triangle. Yeah?
Yeah, why can't you just start your triangle at the very corner and then you're defining your like x vector all the way from the very corner of the square to the center? Even a minus 2x.
I'm not, you mean like that?
Yeah.
That's one of the pieces of this. But you have to define r for every point on the axis. So a good check of, does this give you what you think that it should? If this is just the point right here, does it give me the length that I expect it to? Well, this would be an angle of 45 degrees, right? If it's at the corner. And then in that case, x is 0. So I put in x is equal to 0 here. This gives me a over 2 quantity squared plus a over 2 quantity squared. That gives me r is going to be equal to root 2 times, wait, hold on, let me, this gives me a factor of 4. So this is a over root 2. When I plug that in. And basically what I did is I have a divided by 2 squared plus a over 2 squared, that's a over 4 plus a over 4, which is a over 2, and then it's under a square root, and a squared. So that's why I get an a here and a root 2. And if I look now at this triangle, which is a 45-degree triangle, if this is a length a over 2, 45 degrees, this should be a length of a divided by root 2. So it's a good check to make sure that it's doing what you want, but the important takeaway here is you need to define r as a function of x, because for every point along this axis you have a different r. Okay? Yeah?
When you solved for sine theta, why did you use y instead of a over 2?
I should have. This should be a over 2, because y is equal to a over 2. Yeah, thanks. Other questions? Yeah.
So because of symmetry, would you multiply up?
Yeah, that was the last part. So every one of these sides is going to contribute the same magnetic field because it's the same distance from the center, the wire is. It has the same current, and yeah, and the distance is the same. So ultimately, if I wanted to find B total, I multiply this by 4. Yeah. Other questions? These ones, this is, between this and the infinite line, there's not too many variations for things that I can ask for questions like this with Biot-Savart Law for lines. You have to be careful with the way that you're defining your origin and the way that you're defining your limits of integration. And then the only other problems that I can ask are arcs of circles. You'll see that in the classwork for today, I actually combine the two. So I have this partial arc of a circle and then partial line. But that's basically everything. So if you can do this and make sure that you can think about the limits of integration properly, you'll do pretty well on these questions on the exam. And take the cross product. That's the other thing. Cross product is what's giving you the direction here. Okay. Any other questions about this one before I move on to the second question? Yeah.
It seems like it would be easy to like mix up a force calculation where like the things cancel out with this, just because like the geometry is the same.
Sure. Yeah, so if instead of having currents here, these were lambdas, right? Just charge densities that were stationary, there would be no electric field at the center, right? So you have to, you're right. Your intuition is good to say that, there is some symmetry here, but that doesn't mean that things cancel. In this case, this actually means that they add together. Yeah. Okay. Anything else on this one? Okay. So the second question that we had here was actually just to work through the example that I wrote in the notes. And so that's to say, if I have some current I going to the left like this, I want to find what the magnetic field is everywhere if this wire has some radius of A. Okay. Now, the reason why I can use Amperes Law here, and I could use Biot-Savart here, it ends up being complicated, but I can't use Amperes Law here, is because in order to use Amperes Law, you need infinitely long wires. And I'm saying that treat this as if it's really long in both directions. If you really want to know why that is, I can talk to you a little bit more about this later, but it ultimately has to do with kind of the same thing with electric fields for canceling components and when you can use Gauss's law. If it's cylindrically symmetric, it needs to be infinitely long. Okay, so let's first start by writing down Amperes Law. So this is the integral of B dot dl is equal to mu naught times I in. And there are two regions that I'm interested in finding the magnetic field in. The first region is where R is less than A, and the second region is where R is greater than A. Okay. Now, it turns out that the left-hand side of Ampere's law is going to reduce the same way for both. And so, what does this equation say? Well, it says if I take the magnetic field and I take the dot product between it and some line element, and I add those up over some closed loop, that's going to give me the permeability of free space times the current that passes through the loop. And so just like when we were using Gauss's law, we want to make sure that for whatever surface or loop we choose, we want to do it in such a way that the dot product is going to reduce nicely. And so here what that means is magnetic fields go around wires like this. And so the loop that I want to draw is going to look like that. It's just going to be some circular loop that's centered on the center of the axis here. And the other thing is that I could have the loop going this way, or I could have the loop going this way. You fix the direction that you want the loop to go by applying the right-hand rule in a slightly different way than we've seen so far. And that's just to say that to determine the direction of a magnetic field that goes around a current-carrying wire, take your thumb and point it in the direction of the current, and the magnetic field just goes around the direction your fingers curl. And so that means that for this current going this way, the magnetic field is going to go around that way, which is why I define my loop that way. Okay. So let's evaluate the left-hand side of Ampere's law. And so what we see, because of the choice of the loop that we have, this integral of b dot dl is going to reduce to the integral of b times dl. And because the magnetic field has the same value at every point around this loop, I can pull it outside of the integral. And then I can say that this integral over the closed loop of dl is just going to be b times l, which in this case, because we're using a circular loop, is just going to be the circumference of this circle. And so this is just going to be b times 2 pi times r. Okay? And this actually turns out to be the same when I go around this way too. Okay? Now let's look at how we can evaluate the right-hand side of Ampere's law. So when I'm in the region where R is less than A, not the entire current's not going to go through this loop, right? The loop's smaller than the wire, so it's going to be less than the total current that's passing through here, through the entire cross-section. And so what we can do is we can say that I in is going to be equal to the integral of j dot dA. So the current that passes through the loop is going to be equal to the flux of the current density that goes through the little areas that I have that make up this area, and then sum over the total area of the loop. Okay. So in order to evaluate this equation, I introduced this J, this current density. And so just like when we were doing questions with Gauss's law and we wanted to find Q in for some insulator, we say that this is rho dV. We needed to know what rho was. So here we need to know what J is. And so in order to find J, we can say that dimensionally J is some current divided by area. And if I give you what the current is that passes through this total cross-sectional area of pi a squared, J is just going to be equal to I divided by the total area, which in this case is just pi a squared. Okay. So now that we want to find what Qn is, we can use this J to evaluate this integral, and so, what In is. In is going to be equal to the integral of I divided by pi a squared. dA in this case is going to be 2 pi r dr. We can cancel our pi's. And now, again, when we want to compare this to Gauss's law, this is a very important point. What are the limits of integration here? When I think about the area that this current is going through for R is less than A, where does that start and where does it end?
0 to R.
0 to R. Good. Good. So this goes from 0 to R. And so when I do this integral, I'm going to cancel this factor of 2, and what I see is I in is going to be equal to pi r squared divided by a squared. Okay? I can put this together with the left-hand side of Amperes Law, and what that says in the end is that B vector is going to be equal to mu naught I times R divided by 2 pi times A squared, and then I can say that I can recover the direction that this goes around because I said it was going in some angular direction in the end. Okay? Any questions about this? We'll get more practice with this, but the punchline is, and it sounded like a lot of you guys already got this because it carries over pretty nicely from some of the ways that we thought about Gauss's law for insulators. When I think about what the limits of integration are, I need to think about what the bounds of the loop are. That's really what the limits of integration mean. Is there a question? Yeah.
Where's the theta hat?
Say again?
Where did the theta hat?
Theta hat comes from the fact that I chose there to be some direction for this to go around, and that direction actually went away when I took the dot product. So I just brought it back in the end. Kind of the same way with Gauss's law. If I said the integral of E dot ds is equal to Qn divided by epsilon naught, and say I had a point charge. This radiates outwards. We have some sphere that I draw around this. This ds points radially outward. But when I evaluate this left-hand side and I take the dot product, I get rid of that directional information. And then in the end, I could say, well, I said from the start that E was pointing radially outward. It's the same idea here. I'm saying that I drew this loop like this, and then B is in the same direction as that dl to take the dot product so that I can evaluate the left-hand side. But that information's still there, and I just put it in at the end. Okay? Yeah?
Can you explain to me what dA is defined as, and how you know it's 2 pi or not? Like,
Sure. So I think this might just be something that I'll probably just give you this on the exam, but the way that you can think about this is, say I have a circle, and I want to find what the area of this is by considering some rings, and then adding all of these rings up. So what we're really interested in is what is the infinitesimal area dA for each one of these rings. It has some thickness here of dr, and then it has some circumference of 2 pi r. So that tells me that this is going to be 2 pi r times dr. So that's ultimately where that comes from. You can think about it
for like different shapes, I guess.
Yeah. So and we saw this, and we see it quite a bit. I don't get into a lot of the geometry. I just give you what these things are. This is something a calculus professor should teach you. I don't want to spend too much time on it, but it is an important question. How do I build up this dA? Well, we saw in Cartesian coordinates, dA is just going to be dx dy, right? We remember that? Because we could say, this is a little box, there's a little dx, there's a little dy. We're doing the same thing in polar coordinates, but really, now what I say is, this is some dr, this is some r d theta. And so in polar coordinates, dA is equal to r d theta dr. And what I did here was I integrated over the angle, because there's no angular dependence here, so that's how I got this factor of 2 pi, and now I'm writing it as r dr times 2 pi. It's a good question, but it's not a terribly important point for us to understand where this comes from. Just know that when I'm dealing with circles, like so if I have a cross section, it's a circle. I want to find what the area of that circle is. The area of that circle as an infinitesimal is just 2 pi r dr. Yeah.
What if your current is going radially outward? Is it still 2 pi r dr?
If the current's going radially outward, you can't apply Amperes Law. So there wouldn't be a question like that for Amperes Law. Those are the kinds of questions we could ask for resistance and resistivity. But and try to imagine, and you can think about why it is that I'm saying you can't do that for it going radially outward and do it nicely with Amperes Law. How do I define a loop? That if I had something going with current radially outward, what loop can I draw to consider what the in a way that I could add up all the magnetic field around that loop and have a dot product that was just the product of the two magnitudes of those. I can't imagine it. Civic, what do you think? How would you draw a loop to apply Ampere's law if something's going radially outward? I don't think there's a way you can.
It'd just be a sphere, or like a rotating loop that causes like some sort of like cylinder or.
Well, I mean, you could always draw a loop. It's a matter of is there a loop that you can draw so that the left-hand side of Ampere's law reduces in the same way that I'd erased it now, and I don't think you can. We can think about it, but I wouldn't ask a question like that strictly because it's very difficult to think of a loop that gives you the right properties that allow you to do that. Okay, so the last piece that we have here is to find what the magnetic field is for R is greater than A. Well, we're fortunate here because when we draw that loop, all of the current goes through it, right? So because all of the current goes through the loop, I in is just going to be equal to I in is just equal to I, right? Just the total current. For R is greater than A, right? We see that. We have this loop here, all of the current goes through it. So when I simplify Ampere's law, what I see in the end is B vector is equal to mu naught I divided by 2 pi R times theta hat, okay? Now you might recognize this. Where else did we see this? It was in the notes. It goes back to something we did with Biot-Savart. This was actually, and somebody, you were asking me how did I do that integral? I didn't, I cheated because I knew what the answer was. Because both ways have to give you the same answer. And so if I had an infinitely long wire with current I, and I wanted to find what the magnetic field is by using Biot-Savart, I would get the same answer. These two have to be consistent with each other for the physics to work. Okay. Any other questions about this? Okay. I'll keep trying to think about loops for this, but I don't think there's a geometry that you can use for that. Okay, so go ahead and get started on the classwork for today, and then I'll come and answer questions as you guys have them.